So in today's video, we're going to check the convergence of Newton-Raphson method. So the first thing first, we all know about how the Newton-Raphson method works. We know that there is a term called xn plus 1, there's a term called xn, which is the previous value, and we have a new value which we get, that is xn plus 1, and these are the derivatives of xn. So we know how this method works is that usually with let's say this is the curve. I didn't draw a curve properly, so let me draw it properly here. So if this is the curve, then you get the first tangent. Let us say this is intersecting. I'm not drawn it properly, but let's say this is intersecting at this point. Then you get another point here, and you again draw a tangent, and we do this till we approach the root of the thing. So we do this part, we keep on getting tangents again and again here, then we take that point, we draw another tangent, and we keep on doing this until we get the solution, or until we are close enough to the solution, that is the root. Now we are talking about the convergence of this method. Now we know that Newton-Raphson method is preferred. Why is it preferred? Because its convergence is faster. Convergence is faster as compared to other methods. Now we'll see why this convergence is fast. If you have solved the sum using Newton-Raphson method, you might have observed that in most cases, in 3 or 4 steps, you get the answer and the value starts repeating. So we'll, without wasting any time, we'll go in the proof actually. So let A be the actual root of the equation. So we can say that f of a equal to O. So if f of a is the actual root, then f of a will always be equal to 0 because the root satisfies the equation. Now we'll modify this thing. If a is the root, so actual root, so we'll say what we find in xn and xn plus 1 is the approximation of the root, right? So we can write this that xn is some a, which is the actual root, plus some error en. Similarly, we can write xn plus 1 equal to a plus en plus 1. I hope this is clear till this point. Now we'll substitute these values in the main equation. So you can give these equations numbers like equation 1, equation 2, equation 3, and then show that putting 2 and 3 in 1, but I'm just showing you the main thing, how the proof works. That is why I'm just ignoring those steps. To make it more theoretical, you can obviously write those, and those are considered good if you write. So now we'll substitute this in the main equation. So what do we get after substituting this in the main equation? We get xn plus 1. We know that xn is equal to xn minus f of xn by f dash of xn. So we can write this as nothing else but a plus en plus 1 equal to a plus en minus f of a plus en by f of a plus en. Okay, this is one thing. Now we just cancel this a and a because this is going to go. So en plus 1 equal to en minus f of a plus en by f dash of a plus en. Now we know there's a formula called Taylor's series expansion that says f of x plus a is equal to you can write it as something like f of a plus x f dash of a plus x square by 2 f dash double dash of a, and all these terms here. So that is the first thing. So if you put that, and we'll say we have in this formula, let's say en is equal to your x and a equal to your a in this formula, and this formula, extrapolating both of this, I'm saying let x be en and a be equal to a. So we can write this as en plus 1 equal to en minus f of a plus en. Now f of a plus en I can write as if I say that my a equal to a, this formula ka a equal to this a, and en equal to x, I can write this as something like f of a en minus f of a plus en, which is x en f dash of a plus en square by 2 f double dash of a plus something like this going forward. Okay, and the bottom part, since it's f dash of a, I can write it as f dash of a plus en f double dash of a plus en square by 2 f triple dash of a. Okay, triple dash of a, and continuing with these terms. Now since we have continued this term, I'll continue this equation here. Now since we have got till this point, we have to remember one key thing. Now how did we do this? F dash of a plus en, it was already f dash, so we started with the f dash term. If it's f, we started with f of a. If it's f dash, we started with f dash of a. Okay, now we are going to say that let us ignore en square by 2 and higher terms. We do this for a reason. So en plus 1 equal to en minus, we get f of a plus en f dash of a by f dash of a plus en f double dash of a. So we have the position till this place. Okay, so I'm just going to write it down on another page. So I'll say that my en plus 1 equal to en minus f of a plus x f dash of a, and I have something like f dash of a plus x f double dash of a. Let me just verify if it is the case. Sorry, we had taken e, right? So we had en and en here. Now if you just do cross multiplication, simple cross multiplication will give you f dash of a en plus en square f double dash of a minus f of a plus minus en f dash of a. This minus sign will apply to both of these, so this will become minus and minus. So you have this, and simple cross multiplication, denominator will be same, plus en f double dash of a. Now en f dash of a and en f dash of a, these both are going to get cancelled. So what will remain is en square f double dash of a minus f of a and f dash of a plus en f double dash of a. Now we know that we had said that a is the root, so f of a will always be equal to 0, isn't it? So this term is also gone. So we have en square f double dash of a by f dash of a plus en f double dash of a. Okay, and we had en plus 1 here. Now what is the meaning of this is that the error in the next iteration becomes the square of the error of the previous iteration. So the meaning here is that en plus 1 is somewhat proportional to en square. So it becomes the square of the, this is en the whole square, actually not en square, this is en the whole square. Just for the sake of writing, I've written it like this. So the error of the new step becomes equal to the, proportional at least, to the error of the previous step, the square of the error of the previous step. That is why we say an error obviously reduces. So like it's like saying 0.5 square is what, 0.25, 0.025 something, whatever it is. So it will obviously be less than, let's say 0.5 square will obviously be less than 0.5. We're not talking about squares like 2 square equal to 4 and stuff. So we're talking about things like these. That is why we say that the error in the next step is directly proportional to the square of the error in the previous step. That is why we say that it has a quadratic convergence. Quadratic because power is 2. That is why we say that it has a quadratic convergence. I hope this is clear. This is just an example. It's not something concrete. This was just an example which I portrayed here. There's nothing concrete there. This is an example to show that how it has quadratic convergence, and this is how the error drastically reduces in this case. Thank you very much.